Professor Collette. So good morning, and thank you all for coming out here. As he said, we're all really grateful that you took the time to take the trek and are here to listen to our presentations today. So my name is Jonathan Lowry.
I'm Carolyn Kawadi.
And I'm Sirawit.
And our final group member is Luke Haskell, who is actually currently competing in the Collegiate Rock Climbing National Championship. So he could not be here today, but we're super proud of the work he's doing. And we are Team JVR Remedy. We've spent the last couple months designing a low-cost, low-emissions drill ship. Now, you might ask yourself, why low-cost, why low-emissions drill ship? That doesn't really seem to make any sense. But right now, there's kind of a problem brewing in the Gulf. There's about 14,000 wells that are at various states of disrepair and either need to be plugged now or need to be plugged in the coming decades. And right now, there are solutions out there. There are these things called jackups, which can work in water up to about 500 feet of water depth. And they cost a relatively cheap for the oil industry, $200,000 a day. Then there's these deep water drill ships. They work in water 2,000 feet and deeper, but they cost a staggering $400,000 to $600,000 a day to operate. And in this kind of water depth envelope, there's still a bunch of wells that are unaccounted for. There's wells in this range. There's about 1,200 of these wells that are not currently serviceable with these vessels. And so we need an intermediate solution. We need a cost-effective solution for these intermediate water depth wells. Additionally, there's an opportunity brewing. The Bureau of Ocean Energy Management has identified a multitude of sites throughout the Gulf that could be used for carbon sequestration. And the Samsung Heavy Industries is actively developing carbon sequestration storage and injection vessels for the use off of Ghost in Malaysia. So carbon sequestration is coming, and we saw this as kind of an opportunity to bring it to the Gulf. So these two things, a problem of needing to plug and abandon, an opportunity to bring carbon sequestration, brings to kind of what would a vessel look like? What requirements would we need? Now we want to be able to drill up to a 20,000 foot deep well. These are massive numbers. I think they're staggering. Additionally, we want to be able to do that well without any sort of resupply. So that's resupply of materials, resupply of fuel. We want to be able to do it all up around. And then finally, something I kind of want to draw your attention to is, we want to have something called a moon pool. What is a moon pool, you may ask? It's basically a hole in the middle of our vessel. It's a hole through which we can put any of our equipment. So we're going to put drilling pipe, drilling mud, ROVs, anything we need through the middle of this hole, this moon pool in our vessel. And that's kind of something we all like to know about boats. We want to go about 12 knots, staggering pace. And we want to be eco-conscious, considering that we're trying to usher in a future of decarbonization. So altogether, that comes to the JVR Remedy. It's a drill ship operating in that envelope, 400 to 1,000 feet of water depth, max well depth of 20,000 feet, target day rate of about $200,000 a day. And our goal altogether is to remedy the past by plugging and abandoning these wells that are either actively leaking or soon be leaking in the Gulf, and prepare for the future by being a dual fuel diesel and e-methanol vessel, and prepare and bring in carbon sequestration to the Gulf. So altogether, now that we kind of know the what and the why, we'll pass it off to Carolyn to talk about the how.
Thanks, John. Now we know what we want to do, and then thinking about, we know it needs to be a ship, but we don't really know anything else about what our design is going to look like. So our first step is, what does our ship need to carry? So I'm going to walk you through a series of diagrams. There's a lot of information, but really what I want you to take away is the materials we're using and how much of them. So when drilling a carbon sequestration well, the first step is the actual drilling. So we're going to be cycling mud through, so from our ship all the way down to the depth of where we're drilling and then back up. So we're going to need that volume from the down through the drill string and then back up through that outer layer of pipe. The next step in drilling is putting the pipes in. So you'll see we have cascading size diameters of pipes, each going to a specified length or depth. So we're going to use those depths to determine how many segments a 25-foot pipe we need. And the next step in drilling is we're going to fill in some of those gaps with cement just to stabilize the well. But we're just going to fill in mostly the outer layers, and we'll need that volume of cement on board. And like John said, one of our requirements is we want to be able to drill a full well without resupply. So all of these materials we're going to need to have on board at one time. So that's drilling. Our other mission is the plugging. So you'll see our well structure here on the screen, and we're going to be inserting these 3 cement plugs here. So in some cases we might find an abandoned well where there's just a cap and we're able to easily remove that and get right to plugging. In other cases there might be older plugs where we'll have to, those plugs will be leaking or cracked, and so we'll have to drill those out first and then get to the plugging. So in the case where we're drilling, we're going to use the exact same process as drilling a new well, and we'll need that same amount of mud. For the cement plugging, we'll use the same equipment, and then we'll just need those volumes of those 3 plugs. So our other requirement was to be able to plug 5 wells without resupply, but it turns out that the drilling operation just requires so much more materials. We're actually able to plug about 14 wells with what we have. So these are the weights of all of our materials, these 3 materials. And kind of just with that information, we looked at deep water drill ships, and it turns out that from their whole ship's weight, about 25% of that is just these materials. So we took that number and we designed a hull that would be a dead weight of, or displacement of 20,000 metric tons. You can see our hull design here, and it ended up being 128 meters, which is significantly smaller than those deep water drill ships. So we finally know what our ship looks like. How do we do all the drilling operations we want to do? So like John said, we have a moon pool, and we're drilling through the moon pool, which means we're going to need to stay still while we're drilling. We decided for our design condition that we want to operate in, we just took a step above what the Gulf of Mexico current usually is, and you'll see those conditions on the screen. And the way we're going to do that, instead of having mooring lines, which will take a while to set up, especially in deeper water, we're going to be dynamically positioned. So we're going to have 4 thrusters that are able to move, they're able to swivel and keep us in place. We decided to be class 3 of dynamic positioning, which is the highest level, and that requires us to have redundancy so that even if we lose a thruster, a machinery room, or a control room, we're still able to operate without moving off station and disrupting some of our operations. So thinking about the redundancy case, our worst case would be if we lose a full thruster, we still have to be able to operate. So with assuming that we are in the middle of drilling and we are operating, staying on station with 3 thrusters, our highest power load would be 13.8 megawatts, which is about the power of 100 Subaru Crosstreks. And then just consider that's only our highest load. Our typical operation load is going to be much lower. So because of that, we decided to do an electric architecture. So you'll see our one line, and I want to emphasize we have our 2 machinery rooms, again, in case one of them floods, we still need to be able to operate. And you'll see that each of the thrusters are connected to both machinery rooms for the redundancy, as well as our drilling loads and habitability loads. We also have an emergency generator. That's really just because it's a requirement. If both of our machinery rooms are out, we have really big problems. So that's just so that we can get the crew to safety. So now that we know how to power it, what our ship is going to do, I'm going to hand it off to Sirawit to talk about what that looks like.
Thank you, Carolyn. So, given the required materials that we need for our vessel in order to complete its mission, these are the arrangements that we came up with. Given that we have the moon pool in the middle of our vessel as seen here, we arranged the drilling and plugging machinery around the moon pool as seen here, such that everything has easy access to the derrick and therefore to the well via the moon pool. You can also see that on the opposite ends of our vessel, we have our powering and propulsion systems as seen here. The reason for this is that 1, it's due to our DP requirement, but 2, we arranged our propulsion system this way, such that the ship is level with the waterline. As for the deckhouse itself, well, since we are an American vessel, we want to be competitive with other ships so we can attract American crew, and therefore we designed our ship to strictest American standards for our rooms, and thus we came up with a seven-deck deckhouse, consisting of the first deck being the galley, mess, and stores, the second to sixth deck being the rooms for the crew, and the seventh deck being the wheelhouse, aka the bridge. Now, as any good engineer would do, we gotta check whether our ship is safe. So we first check whether our ship passes the regulations, it doesn't flip over when it's in its normal operating condition, which using the US Coast Guard regulations, it does. But the thing is that there's also a possibility the ship could get flooded, could get damaged, so we tested the safety regulations when the ship is flooded for these cases, and using international regulations, our ship also passes. But the thing is that when you have water entering the ship, you add weight, so there's a risk the ship can snap in half if the structure isn't designed well enough. I'm sure there's a particular ship that comes to mind when I say that. So we then analyzed the maximum moments acting on the ship when the ship is in its normal operating condition, when it's intact, as well as when it's damaged. And we found that the maximum moment occurs when the ship is flooded. So we designed a structure that can support that moment. And we particularly looked at our midship section as seen here. And the reason for this is that, one, this is the weakest part of our ship due to that giant pool you see in the middle. But also we assume that if our ship can support the largest moment at its weakest spot, it could support the rest of the moments throughout the rest of the hull. So using the analysis of what we did for a midship section, we were able to pass regulations, so yes, our ship is safe. But going back to the beginning of this presentation, the purpose of the ship was to be low cost. So is the ship actually low cost? Are we profitable? Well, this is the profit outlook for a ship per year for a 25-year operation. You can see originally the ship cost a lot of money due to construction costs and loans, and it still makes a little bit of profit for those years, but because the loans are still carrying over, you still don't make that much profit. But once those loans end, aside from a maintenance period and halfway through the ship's life cycle, the ship is pretty profitable. So our construction cost is $235 million, and we're charging for a ship a day rate of $230,000 a day. So that equates to an internal rate of return of 13.5%. But if you're a government entity, you may not be interested in making profits. You just want to get the job done. Well, if you want to break even without making a profit, you need to charge $159,000 a day. So, in the end, is the JVR remedy an effective solution? Why JVR? Well, yes, the JVR remedy is an effective solution. It's faster than jackups, cheaper than deep water drill ships. It can serve the niche water that's not being served right now, and it's also capable of full well intervention. In addition to its plugging and abandonment capabilities, the JVR remedy is the perfect vessel to spearhead carbon sequestration into the Gulf of Mexico, thus improving the local economy and environment. So essentially, we're remedying the effects of the past while preparing it for a more sustainable future. I'd like to thank the following people below for aiding us throughout this project, and of course the rest of y'all for supporting us throughout our collegiate careers. And given that, yes, this is the JVR remedy, and we will now entertain any questions.
That's a really great question. For those who didn't hear, the question was, what is e-methanol? So in the current landscape of kind of alternative fuels that are being developed, e-methanol is basically a methanol that is created using carbon that has been previously captured. So you take carbon dioxide out of the air, and then you use renewable energy to create that e-methanol. E-methanol is very expensive right now. It's, I think, like 8 times the cost of diesel per unit energy. Regular methanol that's made using like other diesel products is pretty cheap. It's only a little bit more expensive. But we wanted to have kind of a net, not net, a very small carbon impact. Therefore, we wanted to use e-methanol. So we're going to transition to that over time. Any other questions?
So Carolyn touched on the drilling and operation and keeping the boat very steady. Did you guys discuss like if there's any role at different sea states, like having a twin mast damper, or is that all in the control of the drill itself?
Actually, yes, we did analyze the roll period of the vessel. So essentially what we did is that we assumed our ship has build keels, so basically there's long extensions going out towards like the side of the bottom of the ship. And we did a CQB analysis in its operating condition. And we found that for the heat position moving up and down, it meets the regulations that we passed. However, we will admit that it is a little slightly problematic with the roll, even with the build field. But the thing is that we think the solution to that problem is pretty straightforward, just improving some of the arrangements, shading around some stuff. So what's essentially happening here is that our ship's roll is a little problematic because our ship's actually too stable. So essentially what's happening is that when it rolls, we're just immediately snap back and then the roll period just get large, it'll grow over time. So essentially just making the ship less stable is actually gonna make it better, so that would be pretty much the solution. Yes?
Quick follow-up, I'm not too interested, is there like tech in industry that it allows the drill itself to stay steady while the ship rolls? Is there like a couple systems?
So there's like heat compensators and kind of things like that, but we decided that was out of the scope of this project.
One last question? All right. If not, why don't we take a group one more time?